All right, welcome to the kickoff session for the Undergraduate Research Symposium. This is one of the physics optics sessions. We've got 5 talks scheduled. Each one is 15 minutes. That's been allocated 12 minutes for the presentation, 3 minutes for questions. They've given me signs to hold up. When you have 3 minutes remaining of your 12, 1 minute remaining of your 12. When 12 timer goes off, I'll stand up. Please finish as quickly as possible after that so that we can entertain questions, and I can moderate questions. About midway through the question period, the next speaker can come up to begin making sure that their presentation is on there. Any questions before we begin? So when I introduce a speaker, I will typically give name and title, so speakers can take that into account as they get ready to start. Want to open up your... Yep. Right. And our first speaker today is Duc Le. He is working with Mishka Bhattacharya over in the School of Physics and Astronomy, looking at extremal ellipticity, in Gaussian beam propagation. Propaganda? Sorry. I just...
where's the laser point?
There is right here. And it works like this. Sorry, I shouldn't aim at the audience to make it. Yes, it works.
So,
Papa.
this is,
Don't look at it.
okay. All right. Good morning, everyone. My name is Duc, and this summer I'm working on a project about conservation of extremal electricity in an asymmetric and astigmatic Gaussian beam. I'm working with Akif, and my advisor is Dr. Bhattacharya. So let's begin by talking about the Gaussian beam. So, light is both a particle and a wave, and the wave has multiple configurations. It can be cylindrical wave or spherical wave or planar wave. And one configuration that is of great interest to scientists and engineers is the Gaussian beam, because it is often created by lasers. So when you talk about lasers, you think it would be very coherent, very parallel, but in reality, it has to be focused at some point because it's just impossible to be parallel on the way. So that focus point is called the beam waist, and it has a radius of gamma 0. The intensity of the Gaussian beam drops radially by a Gaussian function, hence the name. And here's the equation for the Gaussian beam. It is complicated, but you can divide it into parts. So this is the radial drop in intensity that I talked about. This has to do with the wavefront curvature. So you see here, every point there's a sphere of equal phase, and the radius will also change with z. The beam radius also changes with z. It gets bigger as you go because it diverges. And the third term is the guide phase, which indicates that the Gaussian beam would undergo a phase shift of 180 degrees when it goes past the focus point. And so ideally in engineering, you would want to create a laser of a Gaussian beam that is ideal, which is rotationally symmetric. However, in reality, it is very hard to do so. A real Gaussian beam would be both asymmetric and astigmatic. So the asymmetry is defined by the difference in the wave spot size. So as you can see here, the cross section of the Gaussian beam, well, for the ideal one, it would be circle. But for a real one, it would be more elliptical. And the second thing is astigmatism. So that is the difference in the location of the waist itself. So the size of the waist and the location of the waist would be different. As you can see here, the waist on the x-axis is over here, but on the y-axis is over there. So it's like twisted the beam a little bit. And so that's the 3D representation of a Gaussian beam. As you can see here, the cross section is elliptical here and more circular over here. And so these two properties, the asymmetry and astigmatism, would be the two unwanted properties that will appear in the manufacturing of a laser. And you want to get rid of that. But later in the research, we found that these two variables are dependent on each other, and it is impossible to decrease both of them. So that will lead to some change in the specification of the quality of the laser. So let's move on to momentum of a Gaussian beam. So it comes as a surprise that the momentum of a Gaussian beam, although it seems to be a very basic property, has not been investigated enough by scientists. So I derived some equations for the momentum. So this is the z momentum, which is the momentum in the axis of propagation of Gaussian beam, and it is equal to this. So the first term can be rewritten as h over lambda, and that's the well-known momentum of a photon. And it has a little drop here and here, which is explained by the x and y momentum of the beam found here and here. So the x and y momentum actually is very interesting because it will act as like it will. So you know the Nobel Prize project about I think the optical tweezer, that's caused by the x and y momentum. And when you add them together to find the Pythagorean relationship, it will converge it back to h bar k, which is the well-known h over lambda. And so now we look at the propagation of a Gaussian beam through a lens. So the lens works by, so you see usually the lens, like the converging lens, would be thicker in the middle and thinner as you go radially out. And that difference in thickness will differ the phase of any beam that goes through it. So it will change the wavefront curvature of a Gaussian beam that propagates through it. So that change in wavefront curvature will change the beam waist, gamma 0x and gamma 0y, and also the location of the waist. So because of that, the asymmetry and the astigmatism will also change. But it is found that the angular momentum will remain a constant if the lens is non-asymmetric. So despite the asymmetry and the astigmatism change, it is later found that there's one property that remains a constant, and that will be crucial. So now we talk about extremal ellipticity of a Gaussian beam. So the extremal ellipticity is defined as the difference in the beam radius in the x and y direction normalized. And as you can see here, for an astigmatic and asymmetric beam, the cross section will be more elliptical at some points and more circular in other, or i.e. the ellipticity varies, like in this graph. And in this graph, you see that it will reach an extremal value, so either a maximum or minimum value. So we call that the extremal ellipticity. And according to Low and China, the extremal ellipticity can be related by this very simple relationship with the astigmatism and the asymmetry. And the interesting thing about this property, the extremal ellipticity, is that upon conservation through a lens, despite the change in most variables like the beam radius, the location of the waist, and the asymmetry and astigmatism, this property remains a constant. And that is very interesting. And my main objective is to explain that conservation during the summer. So my advisor told me that there are only three things that are constant in physics: the energy, linear momentum, or angular momentum. And I found that it is the latter that contributes to this. So let's look at the angular momentum of a Gaussian beam. So how to find the angular momentum? So I just apply the angular momentum operator. I square it and apply it to the wave equation, and I arrive at this complicated expression for the angular momentum. That is the angular momentum per photon. That's why you see the h bar here. So this looks very complicated, but I can divide it into two terms. The first term has to do with the difference in the wavefront radius of a beam in the x and y direction, so I call that astigmatism. And the second term has to do with the difference in the beam radius in the x and y direction, so I call that asymmetry. So because the wavefront radius and the beam radius varies with z, the two terms also are z dependent. So I graph them on this graph. So this is the z-axis, and this is the angular momentum contributed by the astigmatism and the asymmetry. So you can see there are z dependent, but there's some will be the total angular momentum is a constant, and that makes sense because the orbital angular momentum of a photon should not change during propagation because it is conserved. And so I rewrite it in terms of the basic variables of a Gaussian beam, the difference in the wave's locations and the wave's radius in s and y direction. So why is it? What does it have to do with the extremal ellipticity? So next, I rewrite the extremal ellipticity in this way, and that really resembles the previous expression for the angular momentum. So I can relate them in this very compact form, and that's one of the biggest achievements during the summer. And so because angular momentum is conserved upon propagation through a lens, it has been proven that the extremal ellipticity is conserved. And I also spent some time working on the higher order Gaussian beam. So all of the previous work was about the fundamental mode, but it can also achieve higher order mode, which has more energy and has different configurations. And it is very complicated, and as we have we run out of time, we only go over it if anyone has a question. So long story short, it is found that the conservation of extremal ellipticity also applies for a higher order beam. And so, which means it applies for on most laser beams that is in the Hermite Gaussian mode. So, what is the application of this? So as you can see here, the extremal ellipticity is related to the two unwanted factors of a Gaussian beam, which is the astigmatism and the asymmetry. So as you can see here, these two terms are constrained by a conserved property. So upon conservation through any lenses, which appears in lasers, these two variables are changed, but they are constrained, which means if one of them is high, the other one has to be low, and vice versa. So when we specify the requirements for a laser, usually people will specify that both of these have to be low, but because they are constrained now, we can only specify one of them. As a result, the requirements can be relaxed, which in turn means that the manufacturing cost of ultra-precise micro machining system can be lower because there's less regulations and less requirements for them. So that's the end of my presentation. I would like to thank Dr. Bhattacharya for advising me and Kip for providing me with very helpful graphs. So what questions do you have?
Are there any questions for them? Can you go back to the slide where you were relating the angular momentum to the,
Yep.
to the laser quantities?
Yep, see it.
No, before that.
Oh, before
that
that.
allowed you to get there. Because I guess the question is, you had a conserved quantity that had been observed,
Yes,
right?
yes.
That seemed to be related to geometry, the ellipticity.
Yes,
and then you
yes.
related it to angular momentum of the photons, which is
Yes,
really, really
yes.
cool. Which suggests some connection between the angular momentum and the geometry.
Yes, it is.
And
So as you can see here, the angular momentum is related to the extremal ellipticity, which is a geometrical property of a laser.
So how is the angular momentum connected not to the extremal ellipticity,
Yes.
but to A and omega, the parameters that go into the extremal ellipticity?
Oh, okay. So that was in Low and Kleiner's work.
Uh-huh.
They had some analytical derivation for that.
Mm-hmm.
And actually, it can be found by, so when you write extremal ellipticity, it is defined by this, right? Gamma x and gamma y are z dependent.
And what are gamma x and gamma y?
So they are z dependent. So as you see in the slides before this, you see gamma
That's
is,
what I missed.
yeah, it's over here. It's z dependent. So if you plug into the ellipticity equation, you will have a z dependent.
What's gamma naught? The beam width.
Oh, the beam width, it is a constant.
Okay.
An initial property of the beam.
Okay, so that's how you're connecting geometry
Yep,
to any
yep.
electron. Thanks.
Yeah, and the Gaussian dot actually appears here in the asymmetric.
yeah.
Yeah.
Any other questions? All right, let's thank the speaker again. Thanks.